In our previous video, we talked about the 10 properties that these vectors in R2 enjoy. So I have 2 or 3 comments that I want to make on top of what we just said. One is that the same set of properties are true if you replace the words in the plane with in Rn. So if you talk about vectors in Rn, right, in 3 space or 4 space or whatever, the same properties are going to hold. Okay, I don't think that's too surprising. The second thing I want to say is that in math, we often take an axiomatic approach with how we approach everything. So what I mean by that is that math at its core has a set of assumptions that we're using to start with, and these are the assumptions. This is what all of our assumptions are. We have 10 things here that we're assuming vectors are going to do. And there are certain things that we get as consequences of those axioms. So you want your set of axioms to be as minimal and as bare bones as possible. And so that'll kind of give your work or whatever you're doing or whatever subject you're working on as meaningful, as a productive an interpretation as possible. So if you have as few starting assumptions as necessary, then your theory can be super general. Right? If you have a bunch of assumptions that you're assuming this is how this works and this is how that works, and you have like a million things that you're assuming, you're probably not going to have, that's probably not going to be a very fruitful theory. But if you have a theory with only a few assumptions, then that can be a lot more general. So we want as few axioms as possible. And what I want to point out is that these axioms have consequences. So for example, there is no axiom that says that if I take the real number 0 and multiply it by a vector, I get the 0 vector. That's true, but it's not an axiom. What it is it's a consequence of the axioms. So this is true, but it's not an axiom. So what that means is that it must follow from the previous axioms, because we want our axiom list to be as sparse as possible, to be as small as possible. We want as few axioms as possible is what I mean to say. So how can we prove that using what we know? Well, we can prove that using item number 8. I know that 0 times a vector v can be written, well, I can write the real number 0 is 0 plus 0, because I know that that's true, times a vector v. And what that means is that if I were to take this vector v and then distribute, okay, using property number 8, what would happen is we would get, so this would, I'm jumping ahead here. If we were to distribute, we would get 0 times v plus 0 times v. And so that would be our OV here. Okay, so I've taken this, I've distributed it, and then what this says is that that's equal to what we had started with, 0 times v. And so this tells us, so now ignore the first 2 parts and just look at this part. If 0 times v plus 0 times v equals 0 times v, well, we can subtract 0 times v from itself because we know that every vector has an inverse. And what that tells us is that 0 times the vector v is equal to the 0 vector, because if I take this vector and subtract itself from it, I get the 0 vector. And so we get that 0 times any vector is the 0 vector, not as an axiom, but as a consequence. So again, this is a little bit silly, but this is how we get everything that we know about vectors from this minimal set of axioms.